here, let's look at the ideal solenoid. A geometry for which we can calculate the inductance. As I said, for typical devices you would buy, it's going to be very complicated. You would just measure it. But there is actually one we can calculate it for, and we should do that because then maybe we'll understand it a little better. So we have our circuit here, and this inductor is an ideal solenoid of length L, little l, this big L is now taken, and within turns, not turns per unit length, in turns. Now it's a little bit silly to call it an ideal solenoid when it's not infinitely long, right? If it's infinitely long, the turns are infinitely dense and you get a perfect field inside. What we're saying though is that it's wound very well. And even though it's a finite length, we're going to assume the field is perfectly uniform on the inside. So all that stuff we talked about in the last learning sequence is true. Okay, so let's then see if we can figure out how to calculate the inductance of this thing. So we need our equation for the back EMF created in the solenoid. So we have our definition. It means it's minus L di dt. But since this is a well-defined geometry, we also can do it from Faraday's law, where it's minus n, total number of turns, d phi b dt. Both of those are true. This one's treating it as just an unknown circuit element. This one is treating it with Faraday's law of induction. So the quickie thing then we can do is go ahead and stick these things in the time derivative. We know that they're constant. Let's just stick them in. And we can also just make them both positive to make it pretty. What we'll find is that d of Li dt equals d of n phi b dt. Well, in that case, the thing and the parentheses are equal, right? The time derivative of each of these is equal. We'll say the two things are also equal. So the inductance times I equals n times phi b, okay? And we're trying to solve for the inductance, L. L equals big N phi b over I. And now we can think back to what we calculated for the ideal solenoid. What was its magnetic field? It was mu naught big N I, that was B, and then times the flux, we need the area A. Right, so there's N B times A, and that's over I. Okay. And if we put all that together, then what's going to happen? Let's see. So the I's go away. That's good. The inductance shouldn't depend on the actual current. It should be a constant for the device. We have N squared here, mu naught and A. So the inductance then for this ideal solenoid is mu naught, the total number of turns squared, times the area. So there you go. If you want to make a really big inductor, wrap it around a big area and put in a lot of turns and make it an ideal solenoid. And of course, these trends apply even if it's not an ideal solenoid. You still want a lot of turns. That helps you the most, and you want to wrap it on a fairly large area. So that's the one geometry where we can really calculate the inductance. Other geometries, the fringing fields, make it much more complicated.